Bismillahirrahmanirrahim. Today our topic is Fourier series. Okay, so first of all, let me inform you that there are two types of circuits. The one are the sinusoidal circuits, and the other are the non-sinusoidal circuits. So sinusoidal circuits are signals are those which obeys the function of the sine trigonometric function. It's look like this. Okay, and if we have the waveform like this, so also we consider as a sinusoidal waveform, and we assume that it is actually the shifted version of the sinusoidal waveform. So both of these are sinusoidal, and all of the waveforms other than the sinusoidal are called the non-sinusoidal waveforms. It may patterns anyway, so the all the rest will be called as the non-sinusoidal waveform, whether it is DC or the square waveform. Some of the non-sinusoidal waveforms are have been considered as standard for our calculation. Okay, so a few of the standard waveforms are the DC, the pure DC, the square waveform, the triangular waveform. It's look like a triangle. Okay, on both the positive side and the negative side. The rectified, the full wave rectified, the output of the full wave rectified circuit is just like this. So it is also a non-sinusoidal, and sawtooth because it looks like teeth, the tooth of the teeth of the saw. So these are also the non-sinusoidal waveforms. So these are a few standards non-sinusoidal waveform, and we will apply these non-sinusoidal waveforms in in our lecture. Okay, so let's start. So it's an example of their rectifier circuit, in which we are giving the pure sinusoidal, but the output of this circuit is a non-sinusoidal waveform. So mostly it happens that uh, most of the electrical devices gives the output in the form of the non-sinusoidal form, no matter the signal is sinusoidal or the non, but mostly the output is non-sinusoidal form. So let's have a look on the Fourier series. Fourier was a mathematician, and he represent this series, and according to this series, any non-sinusoidal waveform is comprises of infinite number of sinusoidal waveforms. Means if we have a non-sinusoidal waveform, so there are so many sinusoidal waveforms inside this non-sinusoidal waveform. Okay, so this is actually this is, for example, a function f of t. This is the function of non-sinusoidal waveform. Okay, so the first term of this series is pure DC, represented by a naught, and then a series of the sinusoidal, and a series of cosine. Okay, sine terms or cosine, both of these are the sinusoidal series. Okay, so this the coefficients of the sine series are presented by a, while that of the series of the amplitude of the cosine series is represented by the b. So we can write this in the form of summation a naught plus summation n from 1 up to infinity en sin n omega t plus bn cos n omega t. Okay, so n represents the integer, and it varies from 1 up to infinity. Okay, so this is the squeezed form of the Fourier series. Okay, so it is applicable on the non-sinusoidal but periodic waveform. Okay, the signal, the function should be periodic. Okay, if it is non-sinusoidal and non-periodic, then Fourier series will not be applicable. Okay, so if you want to know the amplitude of these Fourier series terms, means the A naught, A1, A2, and these B amplitudes. So here is the formula. A naught is equal to 1 over t, 0 to t, f of t dt. F of t is function of the non-sinusoidal waveform, while t is the time period of that non-sinusoidal waveform. Time period means time required by a single cycle, time required to complete a single cycle. Okay, so if this one cycle is completed in how much time, that will be our time period. So 1 over t, 0 to t, f of t, we can, by this integration, we can find a naught, means the coefficient of the DC term. Okay, now the amplitude of the sine series 2 by t, 0 to t, f of t. Okay, now this is 2 by t. Okay, and sine n omega t. Okay, and bn is equal to 2 by t, 0 to t, f of t cos n omega t. Okay, omega is the angular frequency. Okay, so let's solve few of the example on the basis of what we have taught previously. So write the Fourier series expression for the following waveforms. Okay, so the first one is a pure DC having amplitude of 20. So a naught is equal to 20 because this is a pure DC. So you will have the amplitude of the pure DC, that is a naught is equal to 20 volts. No sine term and no cosine term is involved in this given waveform. So we will have a zero amplitude for the A and B because no sine and cosine term is involved in this function. Okay, so our answer will be V is equal to 20 volt. Okay, now a pure sinusoidal waveform is given. Okay, it represents the sine function. The amplitude, the peak value is 5 milliampere, means 5 into 10 to the power minus 3 ampere. Okay, so now no DC term is involved because A naught represent the DC, so A naught will be equal to 0. Okay, the first cycle, the amplitude of the first cycle is 5 milliampere, so A1 will be equal to 5 into 10 to the power minus 3. Okay, and the second cycle, the second term. Okay, the second term having a frequency of 2 omega. Okay, that will be actually like this. So the second term, okay, having a frequency, the second cycle will also represent a1. Okay, a2 doesn't mean the second cycle. A2 means the cycle having a double frequency, the second harmonic of this fundamental. Okay, so amplitude of this is not given. In fact, this second harmonic is not given. Sorry, the first harmonic is not given. So and later on are also, so a naught, sorry, a2 to an is equal to 0, and no cosine term is involved. So b1, b2, b3, and b up to n is equal to 0. So the answer will be I 5 into 10 to the power minus 3, and then that is because of the sine term. Okay, now in this waveform, we a cosine waveform but with left of DC term. Okay, left of DC term is also provided to this cosine waveform. It means if originally sorry, this cosine waveform was just like this. Okay, but when DC is added, so it a left is has been given, provided, so it will be just like this. Okay, now 8, the DC value is 8 volt. Okay, so and the net amplitude goes to 12, so the amplitude of cosine will be 20 minus 8. Okay, 20 is cosine plus DC is 20. Okay, so what will be the amplitude of the cosine? Only 20 minus 10, which is equal to 12. So again, the first harmonic b1. Okay, DC term is also involved, that is in order equal to 8, and second harmonic and so on of the cosine is 0, and no AC term is involved, so all of the AC amplitudes will be 0. So our answer will be V is equal to 8. 8 represent the DC term, plus 12, 12 because of this, okay, cosine 12 cos, and 1 omega t, 1 omega t because the first harmonic, okay, sorry, the fundamental, not the harmonic, fundamental. In this also, it is also a fundamental, okay, sorry, I've mentioned it as the first harmonic. It is not the first harmonic, that is actually the fundamental, okay, 1 omega, okay, 2 omega will be actually the first harmonic then, okay. So move on. Okay, now we have to read some about the even and the odd functions. Okay, so what are the even and odd functions? If f of t is equal to f of minus t, means if a function is given, okay, and if we flip it, that function, and it also equal to that original function from which it was made, so then it will be called as even function. For example, if we have this function, okay, so uh, if we flipped it, flipping means rotate by this origin, okay, flip. So after flipping we will get function like this, which is also equal to the original function. So this is f of minus t, okay, and this is f of t. So f of t is equal to f of minus t. So it is we can say that it is an even function, okay. Other example is this, the rectified, okay, function. If it is just like this, okay, so similarly it is also an even function. And if it is like this cosine, it is also an even function, okay. Now switch to the odd function. Odd function means if we flipped it and followed by the inversion on the vertical side, okay, means if it is inverted like this on the y-axis as well, after flipping horizontally, flipped it vertically, okay, just like this, and then after flipping and inversion, we get the same function as it was originally, so the function would be called as the odd function, okay. The example is this sine function. If we flipped it, so we will get a function like this, we will get this, okay, but this is f of minus t only. And if we apply a next step after f of minus t, the next step is minus f of minus t, means you have to multiply minus with this function. Being multiplying with minus means the negative term will be converted to positive term, and the positive term will be converted to the negative term. So f minus f of minus t will be just like this, and this is equal to the original waveform, okay. So we can say that this is actually the odd function, okay. Okay, now you have to mention that whether these waveforms are even, odd, or the neither case. Okay, so the first waveform about which we have to tell that whether it is even, odd, or neither. So this is a sawtooth waveform. Okay, sawtooth waveform. It is just like this. We can also call it a ramp function. Okay, so okay, this is 0. So flipped it, flipped it. When we flip it, we will get this. Okay, this 0. So we will get this. So this is not equal to this one. Okay, this is f of minus t. So it means it is not the odd, sorry, the even. Okay, now apply minus to test for the odd function. So when we so we will get this. This is minus f of minus a, which is again not equal to this. So this is neither odd nor even. So this is the neither case. Okay, now let's check this one. Okay, this is the original f of t. Okay, now check whether it is odd, even, or. So first of all flip it, then invert it, so we will get this same function. So it means this is what, this is the odd function. Okay, you can test it. For after flipping we will get this. Okay, after flipping f of minus t means it is not the odd function. Sorry, it is not the even function. Now test for the odd function. So invert it, you will get the same function as original one. Okay, so this is equal to this. This is f of minus t. This was the test for even function, which was failed. Now multiplying minus with this f of minus t, and this is the test for the odd, so which was passed. We can say that it is an odd function. Okay, now the square waveform. So when we flipped it, okay, rotate this by this way, we will get the same original function as it was. So we can say that it is the even function. Okay, so you can test it for the many functions. For example, this is your homework. mm, okay, whether it is even, or neither case. Okay, now you can test it for this. Okay, so this is the shifted version of this. So both of these are the even function. Okay, you can find the f of minus t, so we will get the same as f of t. So we can say this is the even function. Okay, so we will discuss the Fourier series in detail in our next class. Okay, so after, this is all for the moment. Thank you.